All right, here's our second example problem using integrated rate laws. And this one says the reaction has the following form. At a particular temperature, X original is equal to 0.25 molar. Concentration versus time data were collected. A plot of 1 over concentration versus time, or the inverse of a concentration versus time, resulted in a straight line with a positive slope. So now we got to look on here and we got to find out which one has 1 over concentration versus time, straight line, positive slope. There we go. So we know this is going to be a second order animal. So we're going to be using these equations right here. And you remember the slope is k. So if they tell us the slope, we know k already. So we're light years ahead. So remember, we're going to concentrate on these equations right now during this problem. So first of all, letter A, write the rate law. So rate is equal to k, and then our reactant is x, and it's going to be to the second power because we know it's a second order process. And then the integrated rate law, we copy that right off of here. So use the y equals mx plus b form right here. So 1 over a at a particular time is equal to k times t plus 1 over a original. So remember, we're doing the inverses right there. And then calculate the value of the rate constant. So they tell us the slope value right here, and remember the slope is k. So if we know the slope, we know k, and so k is equal to 0.850, and then that's per molarity per minute. Ooh, I love that they give us those tricky units with the negative ones like that. Letter B, right here, calculate the half-life through the reaction. So now we need to look on here to find the half-life equation. Half-life equations are right here. So our half-life is T1 half is equal to 1 over A original times K. And so they want us to calculate this half-life, so we want to find the T right here. And so 1 over, and then original A right here has told us, well, in this case it's X. I guess I should have used X in here, shouldn't I have? I just copied it right from the other sheet that had A in there. But that's okay. These should be X's. Okay, the X original is 0.25 molar. And then our K is given to us by the slope of the line, which is 0.85, and that is 1 over molarity times minutes. So let's plug those two into our calculator here. Try them on yours at the same time. 0.25 times 0.85, enter. And then notice it's the inverse of that. So I'm going to type in the x to the minus 1 button right there, and then hit enter, and there is my half-life right here. And my unit-wise here, notice my molarity cancels with my molarity, so I'm 1 over minutes, which when you multiply by the inverse, you're going to get minutes, which makes sense because you should have a time. And so this is 4.7 to 2 sig figs, which absolutely fine. Just use 2 sig figs right now. All right, letter C then, calculate the time required for the concentration to decrease to 0.035. So now they're asking for time, and remember, anytime they're asking for time, it's not going to be one of these equations up here because time's not in there. It's not going to be some graphical crazy thing. I know half-life's got a T in there, but you know that's T1 half. And so when they're looking for time, they're looking for the use of the integrated rate law right here because it's got a T in it, it's got a T in it, it's got a T in it. So those are the ones that are going to help you find time. So let's write down this integrated rate law equation right here, and then we're going to solve for T. So 1 over A is equal to K times T plus 1 over A original. So the original, let's see, let's start with this one right here because this is the time that we're interested, the concentration we're interested in. So it would be 1 over 0.035 molar is equal to K, and remember the value of K is given to us here by the slope, so that's 0.85, and the units on that, remember, are 1 over molarity times minutes, and then there is a T, that's what we're going to solve for, plus 1 over, and then this is the original concentration right here, which is 0.25 molar right here. Once again, I used A's here, but I should have used X's because that's what the equation shows, but you get that part. All right, so let's do these on our calculator, and then we'll go through and we'll solve for t. So clear, clear, clear. 1 divided by 0.035. That ends up being 28.6 is equal to, okay, we'll leave this the same. This is 0.85 times t plus, and then 1 divided by 0.25, so that's 1 divided by 1/4, that should be 4. So then we're going to subtract 4 from this side, subtract 4 from this side to get that by itself. So 28.6 minus 4, well, that's obviously 24.6. And then it's equal to 0.85 times the time right here. So then we'll divide both sides by 0.85. And so then we'll take 24.6 divided by 0.85, and we end up with our time equaling 28.9 minutes would be our units on that, because that's what the units are for the rate constant. All right, that's the second example. We'll have one more example of a 0th order in a bit.